Hello, this is Mrs. Sargent, and this is the notes over hybridization from April 3rd. Some of you were at the ACT and so missed this little bit of new stuff to finish out our unit. So a hybrid orbital is simply a mixing of different orbitals together to form a new hybridized orbital. So we need the concept of hybrid orbitals to explain molecular shapes. So we talked about drawing our Lewis structures. We talked about what the molecular shapes are. The hybrid orbitals are what is responsible for forming those molecular shapes. So in order to keep this simple, we had our atomic orbitals, the S sublevel, the P sublevel, D and F sublevel. S had 1 orbital, P had 3, D had 5, and F had 7. When we mix an S orbital and a P orbital together, we get hybrid orbitals. How many ever, the number of the number of atomic orbitals you have is equal to the number of hybrid orbitals. So for example, if you have 1 S orbital and 3 P orbitals, you have a total of 4 atomic orbitals. So that means that we need to have 4 hybrid orbitals. So S and P are mixing together. So that means that we're going to have some SP hybrid orbitals. And so if we have 4, S is 1, and then we have 3 P, that is going to give us a total of 4 SP3. And so you can see here, it has part of the shape from the P orbital, and this right here, this black dot, is the center, and that's in the center of the S orbital. And so it has a little bit of the P, or it has some of the P and a little bit of the S. And so these 4 SP3 orbitals arrange together to form a tetrahedral shape. And one of the things about the hybrid orbitals is that unlike the atomic orbitals where the S has 1 energy and the P has a higher energy, the SP3 hybrid orbitals all have exactly the same energies. So this kind of normalizes the energies between the hybrid orbitals. So these are the possible hybrid orbitals that you can have. When you think about how many orbitals hybrid orbitals you're going to have, you need to think about the electron domains. So hybrid orbitals, the number of hybrid orbitals equals the number of electron domains. Okay, so if you have 2 electron domains, you're going to have an overlap between the S and the P orbitals. So that is going to give you an SP hybridization. And so there are 2 SP hybrid orbitals. These shapes have to do with the electron geometry. So a linear electron geometry is going to give you an sp hybridization. If you have 3 electron domains, you are going to have sp2, and 3 of those sp2 hybrid orbitals, the electron geometry is trigonal planar. sp3, that's what we looked at on the last slide. This is when you have 4 electron domains, it's going to give you a tetrahedral electron geometry. If you have 5 electron domains, you're going to have sp3d, and that's going to give you a trigonal bipyramidal electron geometry. I'm just going to write this in here, electron geometry. And then for 6 electron domains, you get sp3d2, and that is an octahedral electron geometry. So these are the 5 possible hybridizations that you can have for hybrid orbitals. So the number of electron domains on the atom will indicate the hybridization needed. So for example, if we have this molecule where we have a double bond between the 2 carbon, and each carbon has a hydrogen off of it. So I'm going to just draw this out here so it's a little bit easier to see the molecule. So we have 2 center atoms. So we can look at the hybridization around each carbon. So carbon has 1, 2, 3 electron domains. Remember, the double bond counts as 1 electron domain. So 3 excuse me, 3 electron domains is going to give us an sp2 hybridization for the carbon. And that is true for this carbon as well, because it still has 1, 2, 3 electron domains. So carbon has 3 electron domains. The hybridization must be sp2, which has 3 hybrid orbital domains as well. So the only other thing with hybridization is that we get sigma and pi bonds. So when we have this overlapping shared orbitals, or the overlapping of orbitals, we have 2 varieties. Sigma bonds, so this kind of O with a tail on the top of it, this is sigma. It's a Greek letter for sigma. So sigma bonds, the electron density lies on the axis between the nuclei. So you can think about it as it lies on the bond line. All single bonds are sigma bonds. So this is the molecule that we looked at on the previous slide, where we have the double bonded carbon in the center. Each carbon has a single bonded hydrogen to it. So what this is telling us is that we know that each of these carbon-hydrogen bonds are going to be a sigma bond. Okay? So by looking at a Lewis structure, single bonds, you can determine the number of sigma bonds from the single bonds. Now pi bonds, just like the pi in math, only it's not referring to 3.14, it's referring to a type of bond. This electron density lies above and below the plane of the nuclei. So it is not along the bond line. It's going to be above and below the atom. So here you have an electron density above the carbon and below the carbon for each of these. And that's where our double bond was found, was between the two carbon. So a double bond consists of one sigma bond. Wow. I don't know how to erase that, but that was a really great straight line. So one sigma bond and one pi bond. So a triple bond has one sigma bond and then two pi bonds. That's what you need to know, is that a double bond is one sigma, one pi bond, triple bond, one sigma bond, two pi bonds. The reason for the electron density being above and below the plane of the nuclei is that often your p orbitals involved in pi bonding come from unhybridized orbitals. So there's not as much overlap between different types of orbitals, so they're unhybridized. So we are already, when we were looking at the Lewis structure on the previous slide, we said that we have our carbon double bonded, hydrogen on each, two hydrogen on each, and we said that those single bonded hydrogen, those are sigma bonds. Okay, now we know that a double bond consists of one sigma bond and one pi bond. So one of these is a sigma bond, the other is going to be a pi bond. Okay, so if we want to determine the total number of sigma bonds, we can count up our sigma, 1, 2, 3, 4, 5, and then we have one pi bond, which is what I have here. The 5 sigma bonds are formed from the overlapping of the sp2 hybrid orbitals. The pi bond is from the unhybridized overlapping p orbitals on each carbon. And then we will talk about this slide tomorrow in class. So take a look at this. The main thing is that from the Lewis structures, you can determine the hybridization, you can determine the electron domains, electron geometry, molecular geometry, like I said, hybridization, and the sigma and pi bonds. And that's why we spent so much time on the Lewis structures. We will go through some more examples tomorrow in class, and then we will, and you guys can ask questions about the review. Second half of class, we will start the test, and then you will have Friday to get the test finished up. So if you have more questions between now and Friday, you can come in during GSH or a seminar or after school for the next few days. Thanks, and have a great day.